A wall, the thickness was L. Measure X from the left-hand side, X equals 0. There was a heat flux on the left-hand side, which was constant. Q double prime, heat flux on the left-hand wall. A fluid, blue, I think it was air, was over the right-hand side. Air temperature was T infinity, the free stream temperature of air. Convection coefficient on the right-hand side, H. Thermal conductivity of the material, K. And we were asked to find the conduction in at X equals 0, the conduction out at X equal L, the amount of the change of the energy stored in the wall, E dot storage, and the convection coefficient on the outside. Given, of course, that temperature distribution. We were given that temperature distribution. Okay, so today we're going to continue with this one a little more, things that were not asked in the problem itself. So I'm adding extra stuff to this. Okay, now, he was really kind to us. He gave us this temperature distribution. In the real world, nobody is going to do that for you. You're on your own. You're supposed to be able to derive it or find the derivation. So normally, we're asked to find that temperature distribution and then do things like this. So that's the difference in this problem and a real problem. All right, so how would we find that temperature distribution? Well, we go back in chapter 2 and we have the heat diffusion equation. Okay. It's a steady state? No, there's a storage term. Is it constant properties? I think so. K was given in the problem. Is it 1D heat transfer? Yeah, I think so. The arrow points left to right. Heat transfers left to right, X direction. Okay, so 1D, so all we have here is the second partial of T with respect to X. Any generation internally? No. Q dot 0. Okay. Equal right-hand side is the change in stored energy, 1 over alpha dt d time. That's the governing partial differential equation for the problem. The governing partial differential equation. We can't solve it yet because, as you know from diff-EQ, we need to have maybe initial conditions and or boundary conditions. So in this problem, we do have an initial condition. It says the temperature for any x at time equal 0 is equal to T initial. That means the temperature for any x at time equals 0 is a constant. So the boundary conditions, there has to be 2 because it's a second order equation. Second partial T with respect to x. Second partial means we need 2 BCs. 2 BCs. The first BC at x equals 0. The amount of heat that comes in from the heat source, Q double prime, heat flux coming in, is taken away by convection at x equals 0. That's conduction. BC number 2. At x equal L. The heat that comes to the surface at x equal L by conduction is carried away to the fluid by convection. So it comes in by conduction. is carried away by convection. So now we have a governing equation, and we have one initial condition, and we have two boundary conditions. So we could solve this t as a function of x and time. Oh, it's not that easy, and we don't do things like that in the first introductory course in heat transfer. But that's the way you would do it. That's the problem setup. Okay. Write down the correct governing equation and apply the initial and boundary conditions. Now, if someone asked us to plot temperature as a function of x, 0 to L, let's make it bigger. I think it'll be easier to plot if I make it bigger. We're going to assume that this particular body starts out at an initial condition where the temperature is constant at Ti, and we're going to assume it starts out cooler, and then we're going to apply a heat source to it. Okay, so it starts out cool. So here's where it starts out. T initial. And that's time equals 0. So time equals 0. We know the temperature is a constant at Ti. Now, do what it says. At time equals 0, we apply a heat source to the wall here. Apply a heat source to the wall. And start blowing over air here, hot air. So I'm going to say T infinity is greater than Ti. So here's T infinity up here somewhere. So we start blowing a hot gas over the right-hand side of the wall. So time equals 0. Instant of time beyond that, I turn on the heat source and I start blowing hot air over the wall on the right-hand side. Obviously, the left-hand side starts to heat up. The right-hand side of the wall starts to heat up. The middle of the wall doesn't know what's going on yet. It's in the middle. Its temperature is unchanged right now. Maybe this time is time T1. Maybe it's 10 seconds. Maybe it's a minute. Maybe it's an hour. I don't care. It's a short time after you turn on the heat source and start the hot air blowing over the wall. Both sides have to go up, obviously. Then I wait a while longer. And now this side got hotter. Of course it got hotter. This is time T2. Wait a little while longer. And maybe a little while longer. T3, T4. Wait a little while longer. T5. Wait a long time. T approaching infinity. Oh, a lot of interesting things happen. The left-hand side keeps getting hotter and hotter until it reaches some equilibrium temperature right here for long, long times. The right-hand side keeps getting hotter and hotter until it reaches an equilibrium temperature after long, long times. But when it reaches that temperature, it's linear. These aren't linear, obviously. The temperatures don't keep going up and up. That wouldn't make a lot of sense. The temperatures don't keep going up and up. If I take a heat lamp and put it on this wall right here, I shine a heat lamp on the wall. I say, all right, initially that wall is at 75 degrees Fahrenheit, TI, constant through the wall from inside to the hall side. Put a heat lamp on here. Go outside and blow hot air on the wall in the hall. Blow hot air in there. Oh, I know what'll happen. This side starts to get warm. The outside starts to get warm. But the middle of concrete, after 15 seconds, won't know the difference. It's still at the temperature 75 degrees. Come back 5 minutes later. 10 minutes, 15, 20, 25, 30. This side gets hotter and hotter. The hall side wall gets hotter and hotter. If I come back in 24 hours, do you think the wall's melted into a glob on the floor? I doubt it. I doubt it. So what had to happen? What had to happen is it came to equilibrium. Yeah, that's right. That's what I'm saying. After a long time, looks like that. Maybe the inside here is up to a temperature of 98, and the temperature in the hall side wall might be 85. Okay. The air outside in the hall, 75. Okay. We didn't say what that was. This was 75 here. Okay. Now, this is important because this is how you're going to work the last problem for homework in Chapter 2, due Wednesday, if you follow what I'm doing here. This is what you're going to be asked to do. They're going to ask you to plot T versus L, T versus X, for a particular problem. Like that, but not exactly the same for homework. Now we're going to plot Q double prime versus time. Time, change your coordinates. Now, on the left-hand side here, that guy's constant. He's constant. The heat lamp puts on the wall a constant heat flux. He's constant. Okay. So here's how much heat at x equal 0. By the way, when I make this sketch of temperature versus distance, x, a couple interesting things here. Number one is on the left-hand side, if I look at the slope at x equals 0, same slope. Here, 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 everywhere, the same slope. Okay? Why? Well, maybe it's here somewhere. Yeah, here's right here. Is that guy constant? Yeah, I told you it was. Is that k constant? Yeah, I told you it was. What does that mean? dt dx at x equals 0 must be what? A constant. Exactly. dt dx at x equals 0 must be a constant, irregardless of the time. Same slope, same slope, same slope. At here, one finger pointing, slope here, slope here, slope. Every one of those slopes at x equals 0 must be the same. Make your drawing. It should show that. Now, I'm going to plot over here the heat flux at x equal L. All right, x equal L. Let's start out for times just past time equals 0. Very short time. Look at the slope. Okay, look at the slope. Here's the equation. Okay, my slope here Temperature is going up as x goes up. Positive slope, positive sign, K, positive sign, negative sign. Uh-oh, the heat flows into the wall. Of course it is. The wall starts off cool, and the hot air blows over it. Yeah. So it starts off negative, down here somewhere. Big negative, big. That's a big slope. Temperature changes big with x. Watch my hand. Time T2. Time T3. Uh-oh. Time T4. 0. It starts off with a big positive slope. It gets smaller and smaller and smaller. Okay. So Q at x equal L starts off big negative and gets smaller and smaller negative until eventually it's 0. Right there, right there. The slope dt dx here is 0. At what time? T4. What time? T4. Okay, now, keep going. Now look at the slope. It's going down. Temperature goes down with x increasing. Negative slope. Negative times positive times negative. Positive. The sign changes to positive. Yeah, it does. Obviously, it goes up here and approaches here asymptotically. This is Q at x equal L double prime. Eventually, as time goes to infinity, what comes in the left goes out the right. Of course. After a long time, the amount of heat that goes into the wall on this side goes out the wall on the hall side, if you wait long enough. The slope here are the same. Therefore, the heat that comes in the left-hand side goes out the right-hand side after long times. So your problem for homework, same thing, different picture. It says plot this, then it says plot this. So hopefully that'll give you some major clues about how to work a problem like that. They're not easy. They're somewhat intuitive, but not completely. What else are they good for? Oh, wow. They developed that magical thing we call engineering intuition about heat transfer. If you can sit down and draw that drawing for someone without ever having solved the governing partial differential equation with the IC and BC, that's pretty impressive. I don't do any math, but I've drawn you that plot there. That's pretty impressive. That separates us guys from other people. Engineering intuition, okay? Sit down on the back of a napkin in a restaurant and plot that thing for you. Oh yeah, that's big time stuff. Okay, now you want real answers with numbers? Go over there, start solving it, okay? But if you want to just see what's going on, that's impressive. Okay, let's go on then. I think, okay, we covered that. Right, so those are all additional things. This was not part of problem 231. That's extra I did for you. This is not part of problem 231. I did that for you. And last time we met, we did this stuff down here. Okay, that pretty much wraps up our chapter 2 and gets us into chapter 3. All right, before I move on, anything on this that you want me to go over before I start chapter 3 then? Okay. All right, let's look at chapter 3. And chapter 3 is 1D steady state conduction. Okay, we'll start off with a picture of what we're going to analyze. And what we have here is a wall. Same thing. It's L in thickness. We're measuring X from the left-hand side. There is a heat flux coming in on the left-hand side, Q double prime, in the x direction. Going out the right-hand side, Qx double prime. The wall has thermal conductivity, K. We're going to make the assumption that T1 on the left is greater than T2 on the right. You can work it in reverse and get the same answers we're going to get out of this. Doesn't matter which one you want to call hot and cold. We'll just say T1 is greater than T2. Okay. We pick out the correct heat diffusion equation. Okay, so here's the heat diffusion equation. That was a plus, right, okay. And then we have our 1 over alpha dt time. Okay, 1d. That guy goes to 0. No internal generation. No Q dot. That guy goes to 0. Steady state. That guy goes to 0. I've already assumed constant properties. Because I pulled the k outside the partial sign. So I've assumed constant properties. I've pulled the k outside the partial sign. And the rho c sub p are assumed to be constant also. So constant properties. What am I left with? The partial becomes ordinary. Temperature is only a function of x. So d squared t dx squared equals 0. Solve that guy. dt dx then must be a constant. Call it C1. Solve that guy. T as a function of x equal C1x plus C2. First thing to notice, linear. Temperature distribution is linear. So now I can draw a straight line from T1 to T2. We assumed that back in chapter 1. We said when we solve problem in chapter 1, we're going to assume it's a linear temperature variation. We didn't tell you how we knew that. Well, this is how we know that. Okay, this is the proof. Okay, that's not the solution. The solution is numbers in there. I don't know what C1 and C2 are, but I do know that there are 2 boundary conditions. The first boundary condition, at x equals 0, t equal t1. Okay, put it in here. T1 equal 0 plus C2. Okay, got it. Constant C2 is temperature T1. Second BC, BC number 2, at x equal L, okay, T equal T2. So we have T2, x equal L now, C1 times L, plus C2, but C2 is T1. C2 was T1. Solve for C1. All right, plug them back into the general solution. So now I plug them back in here, and I get t as a function of x equals C1 plus C2. C2 is T1. Okay. Oops, I got to put an X in there. There we go. Okay, now I guess we can, that's all right, let's leave it like that's fine. Okay, let's see, we got that guy, we plugged him in there, T2 minus T1 divided by L, that's C1 and C2, okay. Now, let's take a look at rewrite this guy if you want. You can rewrite it in here. Do we want to do that? Oh, I guess let's go ahead and get Q. Let's get Q. Box him in first. I'll just tell you one thing first. That T2 minus T1, which is bigger? T1. Which is smaller? T2. That numerator is negative. Negative. What does that tell me about what's happening here? Well, yeah. Starts off high and goes down. Starts off high at T1. This term's negative. Goes down. Makes sense. Okay, let me back up a little bit here. I told you that this is the way we engineers usually get the temperature distribution. Nobody in the real world gives you that guy. You're the engineer, you figure it out. Nobody gives you that. Oh, the textbook does in chapter 2. He has to. We're in chapter 2. But in the real world, nobody does that. You, the engineer, have to write this guy down with this stuff here and solve it by some means, analytically, numerically, whatever. And then, once you get that, you can find the heat transfer by this. You take the partial T with respect to X at some particular location, take the partial T with respect to X once you solve this at some particular X location, and that gives you what? The heat transfer. So the correct procedure is, with a problem like this, for instance, in conduction, write down the governing PDE. Apply the correct BCs and ICs if appropriate. Solve for the temperature, and once you get the temperature, solve for the heat flux. That's the way the flow goes. Here we go again. Here's the physical situation. Write down the correct equation. Here it is. Apply the boundary conditions. Here they are. There's the temperature. What's the next step? I just told you. Solve for the heat transfer anywhere you want it. Anywhere you want it. Okay? Let's do it then. So Q equal minus K A dt dx. Okay, dt dx, T2 minus T1 over L. Okay, right. We got that. Okay, minus sign there. I don't like the minus sign there. I'm going to rewrite it. Delta T is hot minus cold, T1 minus T2. That's the heat flow for that problem there. Don't forget, every equation to the right of my hand, my arm, every equation to the right of my arm has to be 1D, no internal generation, steady state, constant properties. Otherwise, you don't get a linear variation. Okay, and somebody said, you know what, that thing looks interesting. They said, that thing looks similar to Ohm's law in electrical circuit theory. because the left-hand side is the electron flow called the current. This is the flow of electrical energy. This is the flow of thermal energy. They're both flow terms. What causes a current? There must be a difference in voltage or a current won't flow. What causes heat flow? There must be a difference in temperature or heat won't flow. This is the driving potential, a change in temperature or a change in voltage. With that driving potential, this is what happens. There's an electron flow or there's a heat flow. So what do we call the denominator in Ohm's law? The electrical resistance. So, surprise, guess what we call this guy? The thermal conduction resistance. Yeah, this is the thermal conduction resistance. Okay, K is watts per meter degree C, so this guy has units of degree C per watt. If you don't like that, it's degree K per watt, take your choice, they mean the same. Degree C per watt, degree K per watt, but that's the units. And then this is how it would look in a graphical presentation. Hot temperature T1, cold temperature T2. This is the resistance L over Ka. And this is the heat flow Q. So we can model a plane wall as a thermal resistance. So I can model this concrete wall as a resistance. What is it? How thick is the wall? I don't know, 6 or 8 inches thick from here to the hall. What's K? Go to the back of the book under concrete. Got it. What's the area? Forget the door. It's the height times the base of it here, the length. That's the area. That's the resistance of that wall. If the inside room temperature is 75, hall side's cooler at 70, I can tell you how much heat flows from the inside of this room to that cold side on the hall side of the wall. It's as simple as that. But you better make sure 1, 2, 3, 4, or it won't work that way. Okay. All right, so that's how we model that. Now, let's take another one. Obviously, that's conduction. Guess what number 2 is? Yeah, you're right, that's convection. So this one is going to be convection. Q equal H-A-T surface minus T infinity. Or Q equal T surface minus T infinity divided by 1 over HA. Analogously, looks like Ohm's law. Conclusion. Therefore, I think that must be something like a thermal resistance. Yeah, it's called the convection resistance. The units, oh yeah, they're still degree C per watt. Must be the same as conduction. You want to draw the picture? Same thing. You've got a resistance model now. These things kind of make, luckily, they kind of make some common sense. If I want to insulate this room from that hall, here's my choices. What do I want to do? If you insulate it, I want to have a large value of that resistance, because a large value of that resistance means a small value of Q. Okay, got it. I want to make resistance large to insulate this room from the hall side. The obvious way to make it a high resistance, make the wall thicker, and that's common sense. Oh yeah, I'll double the thickness of the wall. Oh sure, right, you got it, sure. I think now, if I want high value of resistance, okay, a low value of K, don't make the wall out of copper or aluminum, okay, no. Make the wall out of something insulating. Concrete's pretty good. So, if you want R to be large, you make K to be small. The area of the wall. The bigger the area is, then the smaller the resistance is, the more heat flows. So the bigger, make common sense, the bigger the wall, the more heat flows out of the wall, sure. Makes sense. So these guys do make common sense, these three parameters in the resistance itself. All right, let's take convection. If I want to insulate something from convection, I have a hot gas stream. And I want to insulate a turbine blade from the hot combustion gases. Oh yeah, of course we do. If I want that to be big, okay, then I can make the area small or make H small, okay, for that guy to be big resistance. So it depends, okay. As you blow air faster over a surface, H goes up. If H goes up, resistance goes down. If resistance goes down, Q goes up. Yeah, sure. Blow air at a faster velocity over a surface. What happens? H goes up, R goes down. If R goes down, Q goes up. Yep, more heat transfer. You got a fan in your car under the hood. The purpose of that fan is to make H large, which cuts down on the resistance of heat flow from your radiator fins to the air, because you want to cool that hot water in those tubes in your radiator by air outside. So all these things, in a way, they're somewhat common sense, but the good news is they kind of reinforce our common sense. Okay, now with those models, two resistors, now we can look at what we would do if we put a composite wall in here. So step number one would be a composite wall. Okay, so let's see, I'm going to change my picture here. Yeah, let's see, maybe I want to change it that much. We'll just assume, for argument's sake, you can change it, that T1 is greater than T2. So heat's flowing left to right. Okay, so we're going to model that wall. We're going to model it by equivalent thermal circuit. So we're going to draw the thermal circuit, which means use these resistances. Okay, we'll start on the left at temperature T1. As we move to the right through the wall, we go through material A by conduction. conduction. Over there, conduction, resistance is given, L over Ka. Here's the resistance, LA over Ka, area of A. That gets us to that point, where my fingertip is. Now we go through material B to get us to the right-hand side of this composite. That goes by conduction through material B, LB, KB, AB. And that gets us to temperature T2. And the heat flow, of course, is Q, and the heat flow coming into the circuit is Q. I'm doing it just like I would do a DC electrical problem. Just like I do a DC electrical problem. Analogous to that. So, if I want to find Q, I take the driving potential, the hot temperature T1 minus the cold temperature T2, divided by the sum of the resistances between my two fingertips. Okay. LA over Ka, area of A. LB over KB, area of B. There's the heat flow in watts. But I can also notice that in the picture here, the area of A equal the area of B, so I might as well just get rid of that and just call it A. Okay, I'll call it A. Now I'm going to divide through both sides by that area A. By the area A. And there is my equation for that wall composed of two different materials. Oh, maybe A is a sheet of aluminum, 1 inch thick. And maybe B is some kind of insulation, 6 inches thick. How much heat goes through the aluminum insulation composite. So that's how we'd use that equation. Now, notice that the same Q goes through here, and the same Q goes through here, the same Q goes through all of those resistances. So, this is a series configuration. So for these two walls, that's a series configuration. All the heat that goes through A goes through B. That's what it says. All the heat that goes through A goes through B. Now, let's say somebody asks you, you know what? I want to know what the temperature is there, TA/B, TA/B. TA/B. Okay, let's see. I'll take all these guys. Okay, I'll take these 2 points right here, my 2 fingertips. I'll take the heat flux. Q double prime equal the hot temperature, T1, the colder temperature, TAB, T1 minus TA/B, divided by the sum of the resistances between my 2 fingertips, LA over Ka. What do I know? Well, first step is find Q double prime for the overall picture. That's the first step. So now I know that. I was given T1, yeah, I know that. I was given LA, I know that. I was given Ka, I know that. I solve for TAB. Okay, that's how you do it. Number one, you find the total heat transfer through the composite, and then you can find the temperature of the interface between materials A and B. Oh, I'll just make something up here. If I assume Ka is greater than Kb, okay, then maybe it'd look like this. Each material is 1D, no generation, steady state, constant properties. So each material, the temperature profile is linear, but they don't have the same slope. No, why should they? For instance, this might be aluminum. Ka is pretty big. This might be calcium silicate insulation. Kb is pretty small. Well, I know through the aluminum, the temperature is not going to change very much. Okay. The resistance is low for aluminum, but the resistance for the insulation, it's big. So the temperature changes a lot across the insulation. Not too much across the metal wall. But they're both linear. They're both linear. Okay. Now, let's see. I'll get up there. Okay, let's do another one. So, of course, what I'm going to do here is I'm going to add convection on both sides. That's the next step. So, let's put on this side, let's put, let me just show it this way. All right, so here's H1 on the left-hand side. Here's T infinity 1, that's the air on the left-hand side. Over here, this is T infinity 2. This is H2 on the right-hand wall. Okay, I'm going to put it here. Yeah, that's fine. It's typically good to start at the hottest side. It makes more sense as you think this through yourself. Start where it's hot. Okay, T1, hot. Let's do it this way. T infinity 1, T infinity 2. This is hot air on this side, cooler air on that side. Heat's going to flow left to right from hot to cold. Draw the thermal circuit. Okay, Q comes in. Then we have, it goes in wall 1 by convection, 1 over H1, I'll call it A sub A. Then we go by conduction through the wall material A, and so that's LA over KA, area of A. And then we go by conduction through material B, LB over KB, AB. And finally, we go out by convection. This is 1 over H2AB. This is temperature T infinity 2. This is temperature T infinity 1. And we have the heat coming in, Q, and because of steady state, no generation, the heat that goes out is the same as the heat that comes in, T infinity 2. Again, it's a series path. That means I add the resistance together to get the equivalent resistance. So the heat flow Q, and Q flows through here, and Q flows through here. In series, the same Q flows through all resistors. So Q equal driving potential, hot minus cold, T infinity 1 minus T infinity 2. I'm going to do it on a double prime area because I don't know the area. It wasn't given to me. Yeah.
Well, if you've got a convection, wouldn't T1 be greater than T infinity 1? Or?
T infinity 1 is greater than T1, is greater than TAB, is greater than T2, is greater than T infinity 2.
So,
yeah.
Okay, all right.
Yeah.
Okay.
Yeah. All right, so the areas are all the same, okay? A sub A equal A sub B, so divide by the area A, just like we did over here. Okay, 1 over H1 plus LA over KA plus LB over KB plus 1 over H2. So for this problem, there is the heat flow. Heat flux, watts per square meter.
How come on the previous problem we didn't take into account the convection?
Oh, I said I put a thermocouple on this wall and I read 78 degrees. I went in the hall and I put a thermocouple on that wall and I read 72 degrees. Somebody gave me T1 and T2. By some means, I don't know how they did. But you're right, typically in the real world, you don't know that. So, but do you know the temperature in this room? Oh, yes, you do. I can hold a thermometer here and read it. The temperature in the hallway? Oh, sure you do. I can hold a thermometer in the hallway. So, yeah, normally you know these two guys because they're easy to find. Most people don't carry around a surface temperature transducer for the walls. No, they don't do that. No. But they can tell you the temperature in the room. Okay, just like over here. What did I say next about this problem? I said, besides finding Q, what else could I ask you? And the answer was, find TAB. Okay, let's find TAB. To find TAB. Okay, remember what I said now. Take your two fingers, where's TAB? Right in the middle. Take your two fingers, put them on here. Okay, the heat flow is Q double prime. Hot temperature, T infinity 1. Cold temperature, TAB. Divided by the sum of the resistances between my two fingertips. 1 over H1 plus Ka over La over Ka. What do I know? I just found Q double prime. I put it in here. I know this. I know this. I know this. I know this. I know that. Solve for TAB. You don't like doing it that way? Put your two fingertips here. You'll get the same answer. Q double prime equal TAB minus T infinity 2 divided by LB over KB plus 1 over H2. You'll get the same answer. Somebody says, yeah, but you know what? I want T1. I want T1. Okay, same rule. Put your fingertips between the temperature you know and the temperature you want to find there. Solve for T1. If you don't like doing it that way, put your one fingertip here. I know T infinity 2. Other fingertip here, T1. Solve for T1. You get the same answer. Okay. So you can find, what I'm saying is, I could ask you 4 things about this problem. First of all, what's the heat flux through the wall? There it is. What's T1? I told you how to find it. What's TAB? It's right there. What's T2? I told you how to find it. I can ask you 4 things about that problem, or more, but normally 4 things like that. Okay? All right. Let's do this one. Okay. Again, a composite wall looks like this. But now we have material A up here and material B down here, and now we have a heat flow Q coming in and a heat flow Q going out. They're the same, steady state, no generation. I'm going to call this temperature T1. I'm going to call this temperature T2. And now some of the heat goes through material A, and some of the heat goes through material B. QB, QA. And of course they recombine over here. Over there. Now I draw the equivalent thermal circuit. Okay. Temperature T1. This is the heat flow Q coming in. Now I have material A and material B. This is, make it double prime. Let's leave it this way. LA over KA, area of A. Down here, LB over KB, area of B. This now becomes the heat flow through material A. This is the heat flow through material B. And of course we know that the total heat flow equal the heat flow going through material A plus the heat flow going through material B. We also know that the length of material A equal the length of material B. I'll put that up here. But the areas are different. Here is the area of A, and here is the area of B. Here's the area of B. Here's the area of A. Okay. You know it's parallel, right? Parallel. Parallel circuit. These guys are series circuits. Series circuits. Where do you get parallel circuits? Well, not quite, but I'll just here's a wall. There's glass in part of the wall, and there's concrete here. If they both had the same thickness, this might be glass blocks, for instance, of the concrete thickness. If there were glass blocks here, then some of the heat that goes through here goes through the concrete wall, and some of the heat would go through the glass blocks. Okay, there they are. Some of the heat from outside to inside goes through the glass blocks. Some goes through the concrete wall. The total is, add them both together. They both have the same thickness, but their areas and their Ks are different. So that would be a wall like that.
Say you had like this wall, the concrete comes out a little further than the glass.
Mm-hmm.
So you just consider K for the concrete and then do both.
Yeah,
okay.
yeah. You have to change that L.
Okay.
Yeah. When you do stuff like that, though, the problem you get obviously is It starts to deviate from 1D.
Yeah.
Even here, do you think that all the heat just goes straight through in one dimension X out there? No, there might be a little bit of heat that transfers from here into here, a little bit. That's the realistic one. But that's not the first heat transfer course you've got either, okay? So in our course, we will assume that we can neglect this as being relatively small, this transfer there. But in the real world, yeah, it's not really a 1D model there. But for our class, we assume it's a good assumption to be 1D. Okay, so I think that pretty much covers that part of chapter 3. So I think we'll stop today, and remember, we passed back homework. Did it get over there? Okay. Passed back homework, and we've got on black.